case you missed it, there was a huge announcement last month.
This is exciting. It genuinely is exciting. It's really good.
We've done it.
Gravitational waves were detected.
You dream of days like this.
Completely elated and excited to be part of it.
This is as big as they come. You know, it really is 100 years in the making.
Physicists around the globe were jubilant. But why should we care? Well, take a step back in time. We know the universe started with a Big Bang. But what did this beginning of time look like? That moment of creation?
Well, sadly, conventional telescopes like these will never be able to see the Big Bang itself, no matter how big and powerful we manage to build them in the future.
Same with radio telescopes. Build one the size of a galaxy, and it still wouldn't be able to see the beginning of time.
It's because no light or radio waves were emitted by the Big Bang, so there's nothing for telescopes to pick up. But there was one thing emitted: gravitational waves.
These are still rippling through the cosmos and washing over the Earth. Build a new type of telescope to pick them up, and we could glimpse the Big Bang itself. And that's one of the reasons for all the fuss last month. America's LIGO facilities detected the first gravitational waves. This is the beginning of gravity wave telescopes. Now, that first detection wasn't of the Big Bang, that's for later, but it was of something breathtaking.
Well, in fact, this is the other exciting part of this story. Not only have we detected gravitational waves for the first time, but the event that produced them has never been seen before. This is two black holes orbiting each other and crashing together.
Never before seen, because these beasts are invisible to our telescopes.
A black hole doesn't emit light. It doesn't emit neutrinos. It doesn't emit any sort of electromagnetic radiation. It is just these two distortions in space which wrap around each other.
The only way to observe these collisions is through their gravity waves. LIGO is an international collaboration, so this is Australia's discovery too. David McClellan leads the ANU team, which has built crucial components of the LIGO detector. But it's a man over in the West I'm keen to meet.
He's in his back shed, apparently.
He lives on this large ramshackle property out the back of Perth. And in Australia, his name has been synonymous with gravity waves since the early 1970s.
Now, this guy is legendary. Even back when I was an astrophysics student, we heard of this researcher over in the West who was trying to do the impossible, find these absolutely tiny gravitational waves. David Blair.
Hi.
Graham Phillips, I found you at last.
Hi, Graham.
Hey, what a fantastic property you've got here. You got a lot of stuff.
Yeah, lots of stuff.
David's been looking for gravity waves since his 20s, and he made this prophetic prediction back in 1980.
We may be able to detect the occurrence of large planets falling into black holes, or even two black holes colliding with each other.
David leads the University of Western Australia's LIGO team. He's excited the discovery's finally been made, but it's also a bit anticlimactic.
Having spent your life all the time hoping and expecting to be detecting something in the future and have it all wrapped up,
To appreciate the immensity of this detection, Einstein predicted gravity waves 100 years ago, although he thought they were too tiny to ever be observed.
They're exactly as Einstein predicted them. They seem to travel at the speed of light, which was what Einstein said.
Others once thought they weren't even real.
Sir Arthur Eddington, the famous British physicist, is also famous for having said gravity waves travel at the speed of thought. In other words, they were just a mathematical artifact. They were in here and they weren't out there.
We now know they're out there. But what are they? Well, David was keen to show me in the university's sacred reflection pool.
Hopefully there are no security cameras here.
There we go.
Ah, look at that. Beautiful ripples.
Yeah.
So that's like the fabric of space-time, this pond.
Yeah, a pair of black holes have just coalesced into a single black hole, and the ripples are spread out through the universe for maybe 1 billion years.
The surface of the pond represents empty space, which is made of nothing. But ripples of gravity, gravitational waves, can propagate out through the nothingness. Indeed, this happens whenever there's a violent event, like the collision of two black holes. For the announcement last month, one black hole was 29 times the mass of the Sun, the other 36.
When they are close, they emit gravitational waves, and the gravitational waves causes the energy of the orbit to get less, and so they spiral closer and closer together. They will finally come to the rapid coalescence and the massive gravitational explosion of gravity waves.
It's that explosion the LIGO detectors picked up. In the aftermath, only a single black hole was left standing, a monster weighing 62 suns. Now, you do the maths. 3 suns worth of mass has vanished in the collision.
So the other 3 solar masses has been radiated away in these gravitational waves.
3 suns worth, obliterated in a fraction of a second.
Gravitational waves they give out are the biggest explosions of energy in the universe, vastly bigger than any other stellar explosion like a supernova or anything, but purely gravitational. They can't be seen by other telescopes.
Kind of eerie knowing the biggest detonations in the cosmos are invisible. Now, remarkably, the frequency of these waves of gravity is actually within the human hearing range.
If our ears were sensitive enough, we'd be able to hear these sounds coming from space. Unfortunately, our ears are about 10 billion times too insensitive for that.
But LIGO's detectors are sensitive enough.
So it would sound something like this. So rising in frequency, rising in intensity. I can't whistle very well, but...
It's known as a chirp. And it's the latest craze in astrophysical circles. The frequency of the chirp steadily rises as the black holes get closer and closer. Here's the real thing. David and his team actually built a gravity wave detector in WA starting back in the 1970s. Its core was a 3-metre-long bar that would vibrate ever so slightly when a gravity wave passed.
And if I tap it, it'll ring, as you can hear, and ringing of this sort will be induced by a passing gravity wave.
These days, it's in a museum. It's an impressive-looking instrument. What's it made of?
It's made of niobium, the best superconducting element that exists.
Pure niobium?
Yes, pure niobium, the biggest piece of niobium in the world.
Unfortunately, it wasn't big enough. It was about 1,000 times too insensitive to detect a gravity wave. But that was solved with LIGO. Instead of a wobbling 3-metre bar, it has a wobbling laser mirror system with 2 4-kilometre long arms. As the era of gravity wave telescopes rolls in, David says it's vital to have a detector here in the southern hemisphere. That way, astronomers can triangulate to find the sources of the gravity waves.
If you have a single gravity wave detector, it's like having one ear. You can tell the sound's coming, but you can't really tell where it's coming from. 2 ears are better than 1. If we had 3 ears, we'd be even better at locating where a bird is in a tree or something like that.
With telescopes listening to the universe dotted all around the globe, who knows what wonders we'll discover out there?